All right, success. Okay, so today we're going to talk about graphing secant and cosecant, which we know from before. Secant and cosecant are the reciprocals of sine and cosine. So when we think about this, I want you to think about what it means to be the reciprocal, right? This idea of this flipping. Okay, so we're going to think a lot about the unit circle today. We're going to think a lot about sine and cosine, even though we're graphing secant and cosecant. So if I want to graph the parent function for cosecant, what I'm actually going to think about is sine. And so I know, based on yesterday, that sine has this idea of the range from -1 to 1, or the amplitude, right? We have a period of 2 pi. We're going to count by pi over 2. So that's where I'm going to actually begin, even though I'm asked to graph cosecant. Now, because I'm graphing cosecant, I'm not actually going to draw in the full shape of sine, but I'm going to give myself an idea of where it should be. I know it starts at the origin, goes to a max, back to intercept, down to a minimum, back to intercept. So if I think about what sine looks like, if I just kind of draw it in dashed, it looks something like that. This is actually not on our graph for cosecant. It's just going to help us to shape it. So now I want you to start thinking about the unit circle. Okay, and now let's think about cosecant. When sine is 0, you get 0. What happens when you find cosecant at 0? It becomes undefined because you're flipping a 0, right? When you flip it, it becomes undefined. And to show undefined on a graph, you create an asymptote. So that means everywhere we had an intercept before for sine, we now have an asymptote for cosecant. Okay, so that's the first thing I do, is I find every intercept and I create an asymptote. Remember, an asymptote is a vertical line, so it should be a x equals equation. We're just going to draw all of these asymptotes in and label them as we go. I like to draw them in with a colored marker, dashed, all good things. Looks nice, okay? Now just continue to think about this reciprocal idea. So when sine is pi over 2, I'm at 1, right? Sine of pi over 2 is 1. So think about cosecant, that's saying you have to flip 1. Well, when you flip 1, what do you get? 1. So that means this is still the same point. Same idea at 3 pi over 2. Sine of 3 pi over 2 is -1. If you flip -1, you still get -1. So those points are the same. Now, we don't really have every point plotted here on sine, but we can think about the circle. So I want you to think about pi over 6. So pi over 6 would be like somewhere here. And the sine of pi over 6 is a half. Agree? But I'm graphing cosecant. So when I flip a half, what should I be at? 2. So that means at pi over 6, I should be up here at 2. Think about 5 pi over 6. At 5 pi over 6, sine is a half. If you flip it to find cosecant, again, you're at 2. So what happens is you create this like parabolic curve that goes up towards the asymptotes. It's not going to touch it. The same idea would be applied down here. If you think about 7 pi over 6 and 11 pi over 6, the sine values are -1/2. But if you flip -1/2, that would take you down to -2. So in our second kind of piece of our graph, we find a parabolic curve that points towards -infinity. The pattern that this will follow every single time is anywhere you had an intercept, you now have an asymptote. Anywhere you had a maximum before, you now have a minimum and the parabola points up. And where you had a minimum, the parabola points down. Okay, that's happening every single time. That's all you have to remember. In order to have one full period, so graph one full period, we need 3 asymptotes and 2 curves. Okay, that's how you'll know you have it all. In terms of labeling, we started by labeling the asymptotes. We need to also label our min and our max for our parabolic curves here. So 3 pi over 2 negative 1 and pi over 2 positive 1. And then I also want you to label the function itself anywhere on the graph. So y equals the cosecant of x, this was. So it's nice because you're reviewing graphing sine and cosine. You just have to remember that you're having to do this reciprocal, so this flipping idea of all of those solution points. Yes? Didn't I say that what? The increasing will start with? Oh, no, it's still a y equals. Or you could use function notation too. Okay. So now let's think about secant. So secant is the reciprocal of cosine. So that means now I'm just thinking about how to graph cosine instead. That's where I begin. So again, cosine would go up to 1, down to negative 1. The period is 2 pi. I count by pi over 2. Remember that cosine starts at a maximum, intercepts, minimum, intercepts, maximum, right? It forms that kind of U shape. I'm just drawing this in dash to kind of guide me when I'm graphing secant. I'm going to apply the same idea. So anywhere I had a 0 for cosine, when I flip it, it will create an asymptote. So I'm going to have an asymptote at pi over 2. And also at 3 pi over 2. Remember, those are x equals. What do you notice about this graph compared to cosecant? What is this missing? That third asymptote. So at that point, you're just going to decide whether you want to extend to the left or extend to the right. I have more room on the right, so I'll probably just go to the right. It doesn't matter which way you go. It's your choice, but you got to go one way or the other. And when you expand or extend your graph, you're just counting by that same jump. So if I just take that kind of further, I would be at 5 pi over 2 here. And then my cosine graph would extend down to touch there at 5 pi over 2, which is going to create that asymptote I need at 5 pi over 2. It doesn't matter if you extend to the left or to the right, you just have to choose one way, okay? It follows the same pattern. Anywhere I had a minimum before, it becomes the maximum of that curve, and you extend to the asymptotes, and then vice versa for the max. You want to label those points and your function itself. Yes?
For the parabolas, do we have to find 3 points for each, or just?
You actually don't have to find any points. You could, but you don't have to. It's just the idea. It's like, just know the pattern. It's quicker. Okay? Questions? Okay, so now these are the parent functions. Let's kind of see what happens when we do a little bit of changing. Okay? Oh, you know what? I want to talk about something else before I turn this. So with sine and cosine, we talked about amplitude. We kept using this word, the amplitude, and it represented the height of the wave, right? From the middle to the top or the middle to the bottom. And so you could define it. It was really clear. But now what happens with secant and cosecant is you're extending without bound to infinity or negative infinity. So there's no distance to be measured. So you'll notice I don't talk about amplitude anymore because it doesn't exist. So like if you look at example 3 and we see this 3 here out front, this now is just referring to this idea of a vertical stretch or a vertical shrink. Okay, so you won't hear me talk about amplitude because there's no way to measure a distance. There is no wave to measure. Okay, When we have a problem like 3 cosecant of pi x, I'm not going to think about that at all. What I'm going to think about is the sign first. And so I know, like, I'm going to have to go up to 3 and down to -3. I also want to think about the period. So the period here, I'm going to take 2 pi divided by my b value, which is pi, which means I'm going to have a period of 2, which is saying you have to do this full pattern within 2 radians, okay? I'm going to think about the jump. So I'm just going to take 2 divided by 4, so that means I'm going to count by 1/2. I'm still talking about radians, I'm just not in terms of pi this time, that's all. So I'm going to have 1/2, 1, 3/2, 2. Thinking about sine, sine normally starts at the origin, max, intercept, min, intercept. You can draw this in dashed, or you can just use those points to guide you. It's up to you. It's really not part of the graph. It just helps to shape it. And then we draw our asymptotes in. So everywhere we had an intercept, I will draw an asymptote, label it with an x equals equation. Make sure there's arrows on the ends, because these are lines, they extend forever. And then I'll have another one at x equals 2. And then I follow the same pattern. Where I had a maximum becomes a minimum of the parabola. Make sure you have arrows on the ends. Make sure it approaches the asymptote, doesn't touch them, and then label your points. Finally, your function, anywhere on the graph. Oh, there was a 3 here. Questions? Let's try it one more time with secant. Okay, so again, when we do secant, all we're thinking about is cosine. So originally, I'm going to think about cosine and the types of transformations I would have. So I'm thinking about 2 cosine of x plus pi over 2. So I notice this is going to go up to 2, down to -2. I don't have a different b value, so I'm just going to count by pi over 2, and the period is 2 pi. Another thing I notice about this equation is I'm going to have to move left pi over 2. So I'm going to extend my graph to the left because I need to shift everything to pi over 2 to the left. So this is going to go into negative pi over 2 here. So I start by graphing cosine. So cosine starts at a max, but I'm going to shift it to the left. And then it goes to intercept, minimum, intercept, max, forming that U shape. Again, what I notice is that those intercepts, I'm going to have my 2 asymptotes, but with secant, you'll never have enough. You have to extend in one direction or the other. This time I'm going to extend to the right, and again, it's just because that's where I have the space. It doesn't matter which way you go, it's your choice. I only have to extend one more jump because that will be my next intercept. So that third asymptote should be at 2 pi. Drawing your curves, you need 2 full curves. Don't give me halves. And then 3 pi over 2. Positive 2, and that one points up. Label your function. I want you to think about this for a second. If this graph originally, let's say, was minus 10, okay, that would be saying take the graph and move it down 10, right? So my original function for sine I'm sorry, cosine, would not have intercepts anymore. I wouldn't see them. We have to remember that an asymptote's undefined all along that line. So you have to imagine where those intercepts would have been, and that's where you would still have the asymptote. So even though you might not see an intercept originally for sine or cosine, you need to think about where they would have been before that shifting of up or down. Does that make sense? Okay, any questions? All right, then you know cosecant and